You got it? All right, I'll start. Heavenly Father, we thank you for this day. Thank you for these students. Just pray to bless this class. Help us to just understand as much of the material as we can today. And again, just to encourage these students just to do their best for your glory each and every day, Lord. In your name I pray. Amen. I'm going to start with this theorem, 11.1.3. It says, every non-empty set of real numbers which is bounded below has a greatest lower bound. All right, so the proof goes like the following. Let's let S be a subset of the reals. S not equal to the empty set. By the way, this is the empty set. It's the set which contains no elements. All right, so to say a set's not equal to the empty set is just to say something's in there. And suppose there exists n such that n in the reals such that what? N is less than or equal to x for all x in S, which is just to say what? All I'm saying at the moment is that S is bounded below. All right? So S is a non-empty set bounded below. Now, the only thing I know about from base principles at this point is sets which are bounded above. Right? I know the least upper bound axiom for sets bounded above. Right? I know that every set which is bounded above has a least upper bound. I know that. That's basic for us in here. But this isn't that. Right? So how do I connect this idea to that idea? It's pretty simple. What's that?
It's just on the bottom instead of the top.
Right, but how do I get a set which is bounded above if this one's bounded below? Well, crane and bricks. Don't swing this way. I wouldn't sit too close to the window. Let's see here. How about this? Minus S. You could define, I'm going to call it T just to give it a more formal name. This is going to be the set of minus x such that x is an element of S. I would point out immediately this is a non-empty set. Okay? It's a set of negatives of S. It's a non-empty set. And furthermore, I will argue it's pretty easy. It's pretty easy to notice what? Minus n is what? Is greater than or equal to minus x, right? Let me be more specific here. I'm saying n less than or equal to x implies that minus n is greater than or equal to minus x. Right? By properties of inequalities. Thank you. Now, therefore, T is bounded above by minus n. Right? Because this is true for all elements of T. Right? So T is a set which is non-empty and bounded above. Therefore, by the least upper bound axiom, by the least upper bound axiom, there exists, let's say, M, which is the least upper bound of T, right? Such that what? Well, M is greater than or equal to x. Well, not x. What do the elements of T look like? Minus x, right? Minus x for all x in S. It's just a smart way of describing the elements of T. All right. Now here's my claim. I claim that the greatest lower bound of S is in fact nothing more than minus m. Notice, if m is greater than or equal to minus x, that implies what? Minus m is what? Less than or equal to x, yes. Multiply by minus, we switch the inequality, right? But that says that minus m serves as a lower bound of S, right? Now that doesn't yet prove that it's the greatest lower bound, right? How do I prove it's the greatest lower bound? Well, how about this? Let's take any other lower bound. What do you guys want to call it? You can call it anything. I'll tell you what the earlier section called it. They called it W. I'm going to call it W again. Let W serve as a lower bound of S. What does that mean? That means that W is less than or equal to X, right? For all X in S. Nothing shocking here about that. What can we do? Same trick as we've already been doing. Multiply this by minus 1. What does this tell us? Hence, minus W, right, is greater than or equal to X for all X in S. Thus, minus W, right, is an upper bound of what? Of T. Oh, I think I forgot something, right? Which is important. What did I miss? What am I missing? Negative on the X, thank you. Right, minus X is a typical element of T, provided X is an element of S by construction. So, what does that say then? How is minus W related to M? What is M? M is the least upper bound, right? So minus W must be greater than or equal to M by definition of least upper bound, right? Lub. But what does that tell us? This implies that W, right, is less than or equal to minus M. Now I claimed that minus M was what? The greatest lower bound of S, right? I think I've actually proved that now. See, because I've showed you that it's a lower bound, and I've also showed you that if we take any other lower bound of S, right, W, that lower bound is smaller than M, or equal to it. Consequently, minus M is the greatest lower bound. And there you have it. And that's why once we have the least upper bound axiom, we automatically get this corresponding result for greatest lower bound. In fact, you see that if you could take the existence of the greatest lower bound as an axiom, right? And you could prove that the least upper bound exists by almost the same argument. We just inequalities flipped over. Once you have one, you have the other. Any questions about this? So let's see here. Now, there's something I want to clarify from our terminology yesterday that I think I can improve on, and reading the text more carefully as I'm trying to do each and every day, try to really understand the totality of his argument, because he is more careful than other calculus books that I've read. So it's I'm slowly absorbing, and kind of it's dawning on me these things I should tell to you. And one of the things I've learned today, which I'm ashamed I didn't learn before, it's just kind of obvious, is so other calculus books have this habit of saying you can either think of the sequence as a sub n, you can think of it as a function, right? You can think about it as a list of values. So they give you this idea that the sequence is the list of values, right? But I think there's a better thing we can say, which is, okay, so like here's the distinction. A sub n is, of course, a shorthand for a of n, right? That's actually the value of the sequence. This is the value of sequence at n, right? I suppose the sequence itself we almost never talk about directly. Like the sequence is really a function from the natural numbers to the reals, right? But, calling a sequence a sub n is the same abusive language that, if you talk about a function, right? A function goes from the reals to the reals, right? And then its value is f of x. F of x is not really the function. Technically speaking, that's the value of the function when you input x, right? And those are distinct things. F is a rule, a single valued assignment of one thing in the domain, for each thing in the domain to a single element in the codomain, whereas f of x is a formula. But we talk about these things interchangeably. This is our custom in calculus, right? But that's an abusive language. In the same sense, saying that a sub n is the sequence is an abusive language. But it's one we'll make, all right? So it's not bad. You can say that. I'm not saying it's wrong to say that. I'm just saying when you say that, you're making the same confusion as this. It's a necessary confusion, though. Now, here's the confusion we can't avoid. This, a1, a2, and so forth and so on, forever and ever, I would say that it's better to say that that's not the sequence. I think that actually, a better description of this, you know what this is? This is the range of the sequence. Okay? Now, the range of the sequence is a set. It is a non-empty set of real numbers. All right? So if the range is a non-empty set of real numbers, if it's bounded above or below, it's in our house. We can shoot it, or whatever, depending on what state you're in, or country. Maybe you don't have guns. Maybe your government's smarter than our government. I don't know. Whatever. We're here. We have guns. All right. Maybe some of you are even packing now. I don't know. I should be more careful what I put on that test Monday. Let's see here. No, I'm joking, mostly. So anyway, my point was just, I really shouldn't say that this is a sequence. I'm going to try to be careful to say that this is the range of the sequence. Okay? But I will warn you, some people say that that's the sequence as well, but that is also an abuse of language. All right, enough about that. Got that on my system. An example I should show you of a sequence, which we haven't done yet, is this one right here. I'm abusing, again, this is all kinds of abuse today, I'm sorry. But I want this one to start at 0 because, well, that's where it starts. And, starting at 1 is really just a matter of notational convenience for us in here. You could talk about sequences that started at -5 or something if you wanted to. We just say that they always start at 1 for the convenience of our not always. Otherwise, everything we said, we'd have to say, like, the starting point and make it would clutter things. But that said, I do want to clutter this example with this discussion. It's worthwhile. So a sub 0 is 1, a sub 1 is 1, all right? And then the rule for n greater than or equal to 2 is that a sub n is equal to n times a sub n minus 1. This is different than the kind of sequences I talked to you guys about. I didn't tell you guys about a recursively defined sequence yesterday, did I? I did not, did I? No. So this is new for you guys. This is another way you can define a sequence in terms of just like the next step. This is a recursively defined sequence. So like a sub 2, using this definition, would be 2 times a1, right? A sub 3 would be 3 times A2. A sub 4, 4 times A3, which, by the way, is 4 times 3 times 2. And this keeps going. Now, this example is so special, it has its own privileged notation. A sub n is equal to n! Oh, sorry. No, it's n factorial. Sorry, it's a stupid joke that I sometimes forget to say. But, anyway, that's a standard notation. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720. Where did I get to? 5 factorial, 6 factorial is 720, 7 factorial is 5040. I don't remember past there. It gets really big really fast. And a factorial is beastly, all right? So that's an example that we will play with this semester. In fact, it's important. Very important example. All right. That said, we go over here now. So unfortunately, well, it's not a big deal, but I disagree with your book on the terminology, and I'm going to teach you standard terminology. Now, the book says that his terminology is standard, and I just beg to differ. Sorry. I know we paid a lot for this book, but, sorry. It's just not the case. So what I'm going to say is that strictly increasing means that the terms are getting larger, and they're not equal, going from one to the next. Strictly increasing. Now, increasing, on the other hand, you have just that the terms are, getting larger, but they could be equal, going from one to the next. It's possible. For example, a constant sequence would still be increasing, but it would not be strictly increasing. Now, in contrast, Sallis-Hilly says that strictly increasing, he calls that just increasing. And he calls increasing non-decreasing. All right? I'm going to use the terminology that I have here on the left. I will try to use that without exception, okay? So just be warned, I will talk about strictly increasing and strictly decreasing. If you read the text, and you should, keep in mind you have to make this conversion of his terms and my terms. It's not a big deal, but it's something you need to be aware of, okay? So that's why I'm telling you. Now, we both talk about monotonic. A monotonic sequence means that, in my terminology, it's either increasing or decreasing. All right. By the way, strictly increasing implies increasing. Every strictly increasing sequence is also increasing. Every strictly decreasing sequence is also decreasing. That's why part of the reason I like my terminology, which is, by the way, not my terminology. It was taught to me in other course, and you survey 10 mathematicians, I think you'll find they agree. Now, he says, Sallis-Hilly, and the other guy, Mr. E, I forget his name, they say that monotonic is any of these four. And that's equivalent, all right? But, okay. So, one of our orders of business in here is to try to come to an understanding of analyzing a sequence as being increasing or decreasing. This is important because we'll have this bounded monotonic sequence theorem, which will give us the existence of certain limits of sequences based on sequences being increasing or decreasing and bounded in a certain way. And the limits will be connected to the least upper bound or the greatest lower bound. So it's all going to come together, all right? Hopefully today. We'll see. All right, so I want to show you some examples of how to analyze this. Now, what's in red is the definition. What's in green is a convenient way to actually analyze it for a specific example. If you read section 11.2, he's really using these as his go-to way of understanding whether it's increasing or decreasing. All right. So I just want to walk you through an example or two of that section because I think it's important for us to talk about these things. And I'll try not to hurry, which means I might not get to the theory I want to. And if I don't, that's okay. We'll just cover it Tuesday. I'm pretty sure that we'll cover, well, I don't know. If I'm not happy with how much we've covered by Tuesday, I'll push the homework back another day. But hopefully the homework will be due Wednesday. And hopefully we'll have time to talk about it Tuesday. So, all right. Example. A sub n equals to n over n plus 1. All right. So just to get a handle on what this is, you know, we've got a sub n equals 1 to infinity. What does it look like, actually? The range of it is what? It's 1/2, 2/3, 3/4, 4/5, and so forth. He for kicks, lists 99 over 100 in the book, which is kind of fun. I mean, it goes on and on. All right, so that, folks, is the range of the sequence, a sub n. So I'm actually just setting aside this question for a second and just go back to our question last time. Well, what are upper lower bounds for this set, right? The range of the set of values. So I can talk about, I mean, you can see it, right? 1/2 is less than or equal to what? A sub n, which is less than what? 1, yeah? So in particular, we can cipher from this that what? You can just kind of see it. So I'm being somewhat informal in my argumentation here. That's okay. Looks to me like the greatest lower bound of the range of an is what? And the least upper bound of the range of an is what? One half, right? And 1. In fact, you could say that the greatest lower bound is the min, since it's actually attained at n equals to 1. All right, so you guys can tell me, just from looking at this, is it increasing, is it decreasing, is it strictly increasing, strictly decreasing? What's the deal? Strictly what? Strictly increasing. All right, so we want to look at a sub n plus 1 divided by a sub n. What's that give us? That gives us n plus 1 over n plus 2, right? Divided by n over n plus 1. Right? Now, what I'm going to do is algebra. This is really n plus 1 squared divided by n times n plus 2. You guys with me? You know how fractions of fractions work? I hope so. I think you guys know this. I'm going to be optimistic. You know this. You're bored at the moment. Okay, so 2n plus 1. You're like, I am bored, but not for the reasons you list. Let's see here, n squared plus 2n. Okay, yeah, I know. Now, you guys told me it was strictly increasing, right? So that means we're trying to show that the quotient is strictly larger than 1 as we set it up, right? So can you see why this is greater than 1? Why?
Because it is 1 plus 1 over n squared plus 2n.
I mean, that's what it says, but why is that the reason? Uh-huh. Ah, so you're like, I can take this and trade it for n squared plus 2n plus 1 greater than n squared. Now, how do you know you're not changing the inequality? Right, n is positive, so n squared plus n is also positive. I'll buy that. And then what? That's 1 is... So this is equivalent to that. And that is equivalent to this, right? Just subtract n squared minus 2n from both sides. Or to go back, add n squared plus 2n to both sides. So the claim that that's less than 1 is equivalent to the claim that 1 is greater than 0, which I think we can agree with. Right? Yeah, I think so. Now, that's not how I looked at it earlier. Another way to look at this, and I like that, what you guys just told me is very snazzy. I like it. It's good. But another way you could look at this, which might be useful, for our thinking is to just think, okay, well, this is like a positive number alpha, right? And so what you've got is you've got alpha plus 1 over alpha, right? That's the pattern here, right? And it's clear that if you take a positive number and you add 1, and you divide by that same positive number, well, that should be greater than 1, right? Now, if you don't believe that that's basic, then you can trade this for alpha plus 1 greater than alpha, and you can trade that for 1 greater than, it's always 1 greater than 0. Is that right? So, anyway. Yes, sir.
Could you split it up too? You got alpha over alpha plus 1 over alpha?
Yeah. Yeah, there's a bunch of different things we could do here. I would agree. The point, though, is you need some way to analyze it, right? I mean, there's an example. Oh, so I'm burying the lead here. Therefore, what? Therefore, a sub n equals to n over n plus 1 is strictly increasing on the natural numbers. And I say on the natural numbers because, you know, okay, we start by saying, oh, sequence has domain to the natural numbers. But then as you read on, you'll notice that he'll start doing stuff like, this sequence starts at 5, or this sequence starts at 7, or something. And so we actually do conceptually allow for sequences to have a starting point other than 1. But we're so lazy that we only want to prove theorems for sequences that start at 1. I hope you can bear that hypocrisy. All right, another example. Yes, sir?
What did you do with the first step?
That's a sub n over a sub n plus 1 over a sub n.
I think you were that one.
How'd it go from here to here? That's a sub n. This is a sub n plus 1. N plus 1, n plus 1 plus 1 is n plus 2. Mm-hmm. Other questions? So the second example here about increasing and decreasing that I can give you, and I'm just following the book because his examples are great, and why make new ones that'll be worse? Actually, he has a 2. I changed it to a 3. See, I'm very hardworking. So a sub n is 3 to the n over n factorial. I told the earlier section that if you're going to bet on a cage match and you see that like you've got a polynomial versus an exponential, you probably want to bet on the exponential. He's going to beat the polynomial. But if you see a factorial enter the ring, oh man, game over. All right, watch out for the factorial. It's a beast. I mean, it will win. And here's how it wins. So basically, the n factorial is way, way bigger than 3 to the n pretty fast. You guys have calculators. You could try putting in 100 factorial. It will choke, almost certainly. You can't express it. Did it work? Do you have factorial?
9.3 times 10 to the 157.
So which one was that? 100 factorial?
100 factorial.
Let's try 1,000,000 factorial.
It goes up to 130. That's the other reason why.
Oh, you know. You've explored this before. Very good, very good. Now factorials grow like stupidly fast, and they will win. But the question we want to. What's that?
Mine can only explain the 69 factorial.
Only the 69 factorial. Okay. Yeah. So it gets big really, really fast, and it actually this factorial function it plays an important and interesting role in the theory this semester. So we'll see it again. Here's an example, though. I want to show that 3 to the n over n factorial is decreasing. All right. Strictly decreasing for n as long as I start n at 3. If I started n at 1, I would not be able to say it's increasing or decreasing because it would do both, and then it wouldn't fit in. I mean, it wouldn't fit into one of these nice categories. Okay, so I mean, there are certainly sequences that neither increase nor decrease, like that one we looked at yesterday with a funny formula. Remember, the one that kept going back to 1, and then the other number kept growing. That's not increasing or decreasing. It's just, yeah. All right, so we look at the quotient, right? Again, we just plug in n plus 1 into the formula. So this is a n plus 1. and this is an, then we do algebra. So 3n plus 1 over times n factorial, 3n over n plus 1 factorial. Right? Excuse me. Then properties of the exponent, the exponential function, tell me that's 3 to the n times 3. All right, times n factorial. And then n factorial, n plus 1 factorial is n plus 1 times n factorial, as I was introducing in the earlier example, right? That's essentially the definition of the factorial function, the recursive definition, right? So the n factorials cancel, the 3 to the n's cancel, you're left with 3 over n plus 1, right? But we can argue that that's less than 1 as follows. But I'll give you a second to catch up. You guys with me? So we've simplified the formula an plus 1 over a sub n all the way down to 3 over n plus 1. Now we want to argue that if n is greater than or equal to 3, right? If you look at 3 over n plus 1, if I go from here to here, what have I done? I've made the denominator smaller, right? Because 3 is smaller than n, or equal to it, right? And making the denominator of a fraction smaller makes the fraction larger. So I have this is, this 3/4 is larger than 3 over n plus 1. But on the other hand, 3/4 of course is less than 1. Consequently what? A sub n is strictly decreasing. Where? For n greater than or equal to 3 would be the more precise statement there. Es bueno? All right, there's a couple of really, this next example is like really, really easy. A question? Oh, no, not a question. See that? Usually if I see someone doing that, they're a magician. And there's like some coin or something, like I can't do that. My wife does this with her pen. She like rolls the pen over her fingers. Any of you do this? Oh, there's one. In any class. My wife is too good at that. Anyway, it's very disturbing if I watch her. Okay, so this example, I digress. C greater than 1, a sub n equal to c to the n. We can prove that this is, strictly increasing. And it's pretty simple to do that. I look at the quotient, a sub n plus 1 over a sub n. I get c to the n plus 1 over c to the n. Properties of exponents, that's c to the n times c divided by c to the n. I get c. But we assumed that c is what? Greater than 1. This being greater than 1, therefore, a sub n is a strictly increasing sequence. Okay. It's funny, it's for me, it's like logically easier for some reason to look at the quotient rather than to look directly at the question in red here. Isn't that interesting? I don't know, it's easier for me. Maybe, I don't know. There's nothing stopping you from attacking the question directly in terms of the red idea rather than the green one. But now this example is the last example in section 11.2. And he uses calculus to do this example, but I don't really think you need calculus if you just do algebra. So if I look at n over e to the n for n greater than or equal to 1, we look at the quotient, a sub n plus 1 over a sub n. Same song and dance. Move the fraction, the denominator of the numerator to the numerator of the denominator. Move the denominator of the denominator to the numerator of the numerator. Anyway, this. Then properties of the exponential function. Well, e to the n plus 1 is e times e to the n, right? So then you got e to the n's canceling, and you're left with n plus 1 over ni. All right? But you can easily show that n plus 1 over ni is less than 1 by this fascinating string of inequalities, which I would ask the camera to zoom in on for our future reference, because I don't want to spend 5 minutes of class on it again, because it's not that interesting. All right. All right. So there are some examples of increasing and decreasing. That brings us to our next theorem. A couple of these problems I just worked are almost your homework problems. So, all right. Theorem 11.3.4. Every convergent sequence is bounded. And when we say a sequence is bounded, you could think about that in terms of a sequence is bounded if and only if its range is bounded as a set. All right, so here's the proof. Let A sub n be a sequence, a convergent sequence. In particular, let's suppose that the limit as n goes to infinity of A sub n is equal to L, where L is a particular real number, okay? Remember we defined what that means yesterday? Okay, so the limit exists. And to say that the sequence, we're trying to show then that the sequence is bounded. And like I was just telling you, the sequence is bounded. We want to trade that for saying the range of the A sub n is bounded. That's what that means, okay? So what does this entitle us to? Like I can draw a picture to kind of tell you what we're going to do. Once I draw the picture, the proof is obvious, okay? Really not that hard. So here's some not very well equally spaced sequence points. But the point is it's limiting to what? You know, to some value L, right? L. And so you're trying to show the sequence is bounded, right? So what you can do, I mean, you get that what? For each epsilon greater than 0, you can make the tail of the sequence fit within an epsilon band if you go far enough out, if you go far enough out. So we can just say set epsilon equals to 1 as to obtain n in the natural numbers, for which if little n is greater than or equal to n, that implies what? The absolute value of A sub n minus L is less than epsilon, which, by the way, is equal to 1. I mean, that limit existing means it's true for all epsilon greater than 0. I can select some n, right? So in particular, it's true for epsilon equals to 1, right? Now, think about that geometrically. What's that entitle us to? That entitles us to, like, there's some n here, right? And then, so like maybe this is 1 plus or minus 1 in the graph, okay? Here's like L plus 1, here's L minus 1. So everything, basically everything out here in the tail is captured like that, right? They're all bounded between plus or minus L plus 1 and L minus 1, right? Out here we have L minus 1 less than AN less than L plus 1, right? That's what we got out there. If you unwrap this inequality, what does it say? It says minus 1 less than AN minus L less than 1, which, by the way, is exactly that. Adding L. Okay? So that's what we have out there, right? So how do I get a bound on the whole thing? right? Because this guy, right, like A1 could be bigger, A2 could be smaller. I mean, I don't know. Before n, all bets are off. But you know what? How many things are before n? Just a finite collection of things, right? Just finitely many. So what I can do is I can use the maximum function. I can pick out the maximum. I'm going to focus on the upper bound, okay? So I can pick the max of A1, A2, AN minus, rather big N minus 1, and L plus 1, right? And you can easily argue, if I call this thing M, we see that A sub n, right, is less than or equal to M. Well, not even less than, it's just less than M, I think, with my construction. Oh, less than or equal to, I guess, because I put these in here, so it could be equal to one of those, I suppose, principle. But anyway, A sub n is less than or equal to M for what? For all n in n. Which is to say that M is a bound for the range. So the sequence is bounded above. How would you show it's bounded below? How about this, the minimum? So we don't, greatest lower bound and least upper bound, these are fantastic tools for infinite sets. But it's overkill for what we're doing right now, because we're looking at a finite set of values. So there's really no need for such sophistication, right? If I take a list of your grades for test 1, right? There's a max and there is a min. It could be attained more than once in both ends, right? Didn't happen, but could have happened, right? Has happened in previous classes. My point is, that's just a finite list of things. I can just lay them out on a table and pick the ones that's biggest and smallest, right? So I don't need the sophistication of least upper bound or greatest lower bound. Okay, anyway, minimum of what? Of A1, A2, AN minus 1, and what? L minus 1, yeah. And you can say that that will be less than or equal to AN for all n. So there you go, that's a lower bound. So in fact, a convergent sequence is bounded above and below. Yes, sir?
Is the AN just wrote, is that the capital N or is that lowercase?
The lowercase one.
It is? Okay.
This one is the lowercase one. These are on purpose the capital one, because this n is connected to the choice epsilon equals to 1. Big N is the thing that puts the tail of height 2. It bounds everything within height, within that 2-unit high band around the limiting value beyond some point. That point is n, big N. This is just saying for all n in the sequence. Yeah. Now, this alone is not that interesting. What's interesting is, the corollary to this theorem. Do you know what a corollary is? Corollary of 11.3.4. It's almost it's an immediate consequence of this, which is that every unbounded sequence does what? Diverges. Well, and so, in other words, does not converge. In practice, that's a more useful statement. For example, I can immediately tell you things like, so for example, like A sub n equals to C to the n does not converge, right? If C is greater than 1. Because that just increases without bound. It's unbounded. doesn't converge, right? Or other stuff, I don't know, like a sub n equals to n. Doesn't converge because n is unbounded. I mean, all kinds of easy kills here. And that's nice because to actually mess with the definition of the limit of a sequence directly, it's kind of a complicated thing, right? So this is a nice, I don't even have to try these sequence. If the sequence is not bounded, game over, it doesn't converge. It's nice, it's very nice. Okay, a theorem I want to state for you today, but I won't prove for you today, is the next theorem. It's very important. Really, this theorem is in fact the punchline for this whole arc of the course, in some sense. Theorem 11.3.6. It states the following: and a bounded monotonic sequence converges. To be more specific, don't I have till 10:10?
Yes.
Okay. In particular, if a sub n is bounded above and let's see, increasing, which means, right, it could be either strictly increasing, then the limit as n goes to infinity of a sub n is actually equal to the least upper bound of the range of a sub n. And if a sub n is bounded below, and decreasing, then the limit as n goes to infinity of a sub n is equal to the greatest lower bound of the range of the sequence. The proof is on page 541 of your text, and that's probably the thing I'll start with on Tuesday. And it's this beautiful merger of the things we've talked about. It uses that theorem we proved last time about finding things inside the set within epsilon units of the greatest lower bound or the least upper bound. So it's really nice theorem to connect everything together. And this gives us the existence of limits which would be otherwise really hard to get our hands on. Because this is tied to the very properties of the real numbers. It goes all the way down. This is a very basic theorem. The other things we'll learn, of course, in section 11.3 is theorems about like manipulative theorems that can be used for more informal calculations, like limit of the sum of limits, limit of product limits, all that good stuff. Also Tuesday. So thanks, guys. Have a good weekend. I do hope you do better on the test come Monday. Homework due is at the soonest Wednesday. It kind of depends on how Tuesday goes.